Okay guys, in this video I want to look at crossed fields and some examples, different examples of crossed fields. So first of all, what crossed fields are when you have magnetic and electric fields that are perpendicular. Actually, they don't really have to be perpendicular, but most of the examples we'll look at are cases when they are perpendicular, when they are crossed with one another. So it might be maybe the easiest example to start with. We'll just take a look at a bunch of different examples. We could look at like a velocity selector. So let's imagine for some reason, you wanted a situation where you wanted to have only charges with a certain speed were allowed to move through something. So for instance, maybe we have a magnetic field here, B. Remember what the X's mean. The X's just mean into the page. So that's the magnetic field B. And then maybe I have an electric field here as well, pointed in this direction. So the green lines represent the electric field. So here we have the electric field E in green and the magnetic field B in blue. And then we could have a charge moving through this crossed field. So these are crossed fields. And so maybe I have a positive charge here moving with some velocity v. Now, since I hope you can convince yourself using the right-hand rule that there's going to be a tendency, there's going to be a magnetic force when this particle enters the field, as the particle moves through the field here with some velocity v. There's going to be a magnetic force that's directed upward, FB, and you can get that from the right-hand rule, pointing your fingers into the page and your thumb to the right, your palm points up. And then there's going to be, of course, an electric field downward. So you're going to have two different forces here, or electric force rather, downward. So we have the electric force and the electric field. And I want to think about the particular case when they're equal. So we could imagine a situation where you had the force from the magnetic field is equal to the force from the electric field. In other words, QVB, since all of these vectors are perpendicular, we can get rid of the sine theta, is equal to QE. That's the electric force, Q times E. And I lose the Q, and I see that the velocity that is required, the velocity required here, is equal to E over B. And so the only part, this is called a velocity selector, because the only kind of particles that are able to move within a straight line through these crossed fields are the particles that have this exact velocity. If the velocity is more, then the magnetic force will dominate and the particle will move upward. If the velocity is too small, the electric force will dominate and the particle will move downward. So that's an example, a very simple example of a cross field. Let's think about something else. What about like the Hall effect? The Hall effect is an interesting thing. So let's imagine that I have a piece of metal. Or it could be any conductor, really. But so maybe maybe it would be the easiest way to think about this is, let's imagine a wire of finite width. And I've got some current. So this is just going to be like a cross section of wire. Maybe I'll try to draw it this way. So imagine just a piece of wire. So we're just imagining some portion of this wire. And that wire happens to be immersed in a magnetic field. So these blue X's are indicating the magnetic field. And maybe the direction of the current in the wire will say, which is the direction of the moving charges, of course, the direction of the current is this way. In other words, we're imagining positive charges that are moving upward. And if we do this, what we could imagine, or what we could see is going to happen here through what's called the Hall effect, is that as these little positive charges move, what you can see is going to happen is there's going to be a magnetic force. And again, if I use the right-hand rule, fingers pointed into the page, thumb pointed up, there's going to be a force to the left, which means over time, you're going to have positive charges get deflected towards the left. And you're going to end up with a case where you're going to have excess positive charges on one side of this metal conductor and excess negative charges then on the opposite side of the conductor. But the issue here is that when this happens, you get an electric field. So now we have an electric field this way. So we are going to end up with cross fields. And the current will continue to flow until we have a situation where the magnetic force is equal to the electric force, as stated before. And this happens at what is called the Hall voltage. So at the Hall voltage, we get a situation where the potential difference, the voltage between the two ends or the two sides of this conductor, the wire in this case, the Hall voltage is creating an electric field, or the electric field creates the Hall voltage that creates a situation where the magnetic force on the individual charges moving through the wire equals the electric force. It's the Hall effect. There's lots of other examples we could think of. It might be interesting to look at like a mass spectrometer. A mass spectrometer is a device where, and this is, I guess, really, I'm not sure that this is technically an example of cross fields, but it's an interesting example nonetheless. Mass spectrometer is a device that's used to separate out charges of different masses, and specifically, sometimes it can be used to figure out the mass of an unknown sample. So let's imagine that we have a chamber here. Do it in black. You have a chamber, and in this chamber, there is a magnetic field. Here's the magnetic field again, B. Actually, you know what I'm going to do? I'm going to make those, the way I've put the input here, I'm going to make these magnetic fields out. I think that's gonna work better. And then what I've got here is maybe off of this chamber, there's a little opening here, and connected to this opening is some tube, which is connected. This tube here is connected to a battery. So I have a battery out here. Such that what we end up with is a potential difference between the two ends of this tube. So we have a potential difference, which is to say that there's going to be an electric field here, an electric field in here. And again, the blue is the magnetic field. So if I then were to plop down a positive charge here, maybe there's just some random positive charge, and I don't know what the mass of this positive charge is. So I just plop it down here. I don't know. I take something, I want to know the mass of it. I'm not sure what the mass is, but I make it positively charged and I plop it down. And it's going to undergo a linear acceleration. That is to say, it's going to gain velocity through this distance, and we can figure out exactly what's velocity. I'll call that V naught when it enters the chamber. And then when it enters the chamber, it's going to experience a magnetic force, which is going to cause it to deflect. And it will deflect, and it will move in a semicircle. And the distance it travels, we'll call this distance right here, we could call that D. The distance it travels before hitting the screen, this thing we could call the screen. This is the screen here, this surface down here, we can call that the screen. So the distance it travels before coming back and hitting the screen is going to then be related, this distance is related to the mass. And just to be clear about this, what that relationship is, we can see here that the magnetic force in this case is serving as a centripetal force. In fact, it's often the case that magnetic forces act as centripetal forces, and that's because they are perpendicular. Centripetal forces are always perpendicular to the motion of an object, so since magnetic forces are perpendicular to the motion of an object, they're often centripetal. In other words, I could say that QVB in this case is equal to mv squared over r. And of course, if in this case, d is related to r, the radius of that curvature. And so I could find, if I solve this thing for m, I can, if I go up here, I can lose one of these v's. And I can see the mass of the sample then is going to be equal to QBR, that's supposed to be a B, QBR divided by V. And so then if I know the magnitude of my magnetic field, if that's something that I know, and I know the charge that I've given the sample, and I know the velocity that it gains through the linear acceleration, and I measure radius, so now if I just measure the R here of the motion through the mass spectrometer, then from that I can determine the mass of the sample. And that's the basics of how a mass spectrometer works. I think maybe I'm not sure, maybe I'll talk about one more example, which was the something called a, let's go down here. This is a slightly more exotic example, but this is what's called a particle accelerator, a cyclotron. Sometimes you want to take a charged particle and you want to accelerate it. And you want to accelerate it very, very quickly. Now, one thing you could do if you wanted to accelerate a particle, maybe I'll note this over here, is you could just do a linear accelerator. That's, by the way, this thing over here was a linear accelerator, right? You just take a long tube, here's our long tube, and you connect both ends of the tube to a battery, and so then you can get a linear acceleration. The problem is if you want, there's a relationship between how fast the particle accelerates, or the final velocity. In this case, there was a relationship between V naught and the length of this chamber. And that means if you want V naught to be big, since V naught is related to distance, I'm calling it this D, since V naught is related to the distance, if you want to make V naught very, very large, in other words, if you want to accelerate this particle to a very large speed, you need a really long tube, and that is not always practical. So then at a certain point in time, people started using the cyclotron, and this was to really, in a compact way, generate enormous accelerations. So this is the way the cyclotron works. We take two hollow metal hemispheres. And I want to just be clear about what this is. This is a hollow metal hemisphere. In other words, if we were to take a side-in view of this thing, we would see it would look like this. You'd have if we were to look in, for instance, if we were looking in that way, looking in, we would see that this is hollow inside, like this. So that it would be solid. There's solid metal walls here, but it would be hollow inside. Like so. And what we're going to do here is we are going to create an external electric field. We're going to immerse this thing in an external electric field. So we have an electric field, E. Like so. And then a magnetic field, we'll have a magnetic field here. Again, so these fields are crossed now. And then what I would do is I might take my little particle, and I'll do green for this, and I'd take my little positive particle and I'd put it right here. And that little positive particle would accelerate due to the electric field here. It would speed up, it would gain energy due to the electric field. But then something interesting happens when it enters this hollow metal hemisphere, semicircle thing. This thing is, by the way, it has a name. They're called Ds because they look like the letter D. That's a D and that's another D. When it enters the metal D, because the D is metal, the electric field inside, if we're inside this chamber in here, the electric field inside is 0 by Gauss's law. So once the charge enters one of the Ds, if the charge is in here somewhere, there's no electric field. There is, however, a magnetic field, and we see that what's going to happen is this magnetic field is going to cause circular motion, just like we talked about before. The magnetic field creates a centripetal force. And then the particle emerges on the other side, and what happens is now the electric field has to flip. It has to switch the direction of the electric field now. So this electric field, I should have noted this earlier, is variable. It keeps oscillating. So this is an oscillating electric field, meaning it constantly flips back and forth, back and forth, back and forth. And so if we go back into here, so by the time the particle emerges, the field has flipped, and now it undergoes a linear acceleration in this direction. So it's going a little bit faster, which means now it's going to move in a circle of slightly larger radius. And then again, the electric field switches and it gets accelerated further, and now it goes in a bigger circle. And again, the electric field switches and it accelerates again in a bigger circle. And you can kind of see how this works. And what you can show, and I'm not going to bother to do this calculation out right now, but what you can show that's interesting is that the period of the motion is constant. In other words, the rate at which you need to constantly switch the direction of the electric field, that rate is constant. So even though the particle keeps moving through these larger and larger paths, right? These circular paths get bigger and bigger and bigger, longer and longer and longer, but the particle is going faster and faster and faster. And it turns out that it takes exactly the same amount of time for the particle to undergo each of these semicircular movements. So all of the times here, all of these periods are the same. And so all you need to do is have this electric field oscillating back and forth at a set frequency, and this particle will keep accelerating, accelerating, accelerating. And using this method, you can accelerate particles to enormous speeds. Turns out that relationship only lasts until a certain point. Once the speed of the particle gets big enough, then actually the period ceases to be constant due to some relativistic effects, and then you have to do some more use some more magic in order to make this process continue to work. You have to have the oscillation varying, but we don't need to get into that detail here. So that's a cyclotron, kind of another example of cross fields. So these are all examples of cross fields, which are again relating the electric field and the magnetic field to one another.